Okay, let's get started. This is the 342 Bootup. My name is Peng Du. I'm a part-time instructor at UW Bothell. Here is some information about myself. My day job is I have a small startup called Paxio. This is a URL if you're interested. The programming language I normally use is mostly Java. I use a lot of Bash and C++. I use that in one of my project in my last job. And so that's pretty much it. The 342 has this goal from the school. I'll give you a second to read. And the key question I want to ask is why C++? In my teaching, normally the way the material is arranged is it's pretty much the same content in terms of data structure, algorithms, all those things. Those are pretty much the same as in 143 class. For example, array, linked list, binary tree, sometimes a little bit of map. In terms of algorithm, that's binary search, sorting, and with search, there's other kind of search. I call this one is sort of a random search where there's not really a pattern in terms of how things are searched. And there's also a sort of locality-based search, or there's some pattern in terms of search, which means some item is searched more often than the other. So some kind of cache would be involved in that. But other than the programming language used in 342 or 143, those are the same content. Then my question, at least from you to you guys, is if that's the case, why are we using C++ to learn this stuff again? You may have your answer. Here is my answer, and the reason I want to talk about this before going into the technical part is I want to set a tone for just this whole 342. It's really for us to learn a bit more about the computer system. And C++, in my view, is you can think of that as a window or as a tool. By using this tool, by looking through this window, we get to see a little bit more details behind the scene, behind the compiler, behind the IDE. It shows us how for example, the memory system work a little bit. And so C++ really is just a tool here. So our goal here is not really to be the expert of C++. In fact, it might take years for someone to become the expert of C++. That's not really the goal here. The goal here is to be able to write, be able to work with those same data structure algorithms through C++, and in the process of doing this, we get to learn more about the system so that if you move on, for example, the memory system, you get to learn a bit more caching, a different level of cache, different performance in different cache, and the process and all those things. So the more you advance in the CS in this CS journey, you learn more and more about the system, and coming back, all those knowledge, all those additional knowledge would come back and help you understand more about the code, and so that you can write much better code and solve much better problem. Speaking of that, the answer I give to the question of why C++ is really three. I call this CAP. I came up with this while I was driving one day. C stands for critical thinking. So when we were writing C++, there are small things for us to debug where we have to deal with memory, which we are going to talk about. And we need to understand some kind of basic logic, and together with the additional part that's not in Java, then we have to learn the critical thinking process. For example, if you see a certain error, there might be some certain reason, then you based on the information you get from the IDE, you could try a few things to figure out what was the issue, what's the cause, what's the root cause, what's the symptom, and all those things. So the critical thinking is the first one. Second one is appreciation. Appreciation just because when you're writing C++, you have to know a bit more about the system. And the more you know about something, then you get to appreciate, you understand the beauty of a certain, for in this case, the design of the computer, the design of the operating system, how the memory space is managed, how the memory system is designed. All those things, the more you know, the more you would appreciate that. A quick example here for me, I'm also a photographer on the side. And one of my way to learn photography is not really just taking more pictures. That's something you have to do. But other than that, I would go to the painting world. I would go to the museum and I would go learn how to paint stuff. And by learning that, I get more intimate ways, colors, light, and you get to see more about all those masterpieces. And once you have done that enough, you know how, for example, even a small shadow in a painting, if you don't have the training, you would not notice. You will see that the painting looks nice, but you will not understand why it looks nice. But having those intimate knowledge of color and how they, for example, put the highlight to be a certain color, and in contrast, they put a shadow to be a certain color. I get to see that, and turning back to my photography, it helped me understand if I see something or if I want to make a picture look good, what are the possible direction that I could go with. Those knowledge come from my appreciation, my understanding, and my knowledge of the painting world. So that's A. P is problem solving. Problem solving means now that we understand more about the system, we can solve more problem. We can solve harder problem or problem that we cannot write with a script. With a higher level language, C++ is sort of a lower level language. Even comparing to Java, there are problems that you can solve with C++ that we cannot solve with Java. For example, mathematical libraries like LAPACK. That's originally written in Fortran, but eventually people start to write C and C++ for them. You're essentially working with matrix every milliseconds in the CPU, every millisecond counts. For that kind of application, we have to understand how the cache, different layer of cache works. Of course, we have to understand the math part. But at the end of the day, when we turn that into the code, we need to use something that we know and we can control the performance. And for that purpose, we cannot use Java. C++ and C are the natural choice. So using C++ at least give us all these different benefits in addition to giving us a way to understand the system more. Hopefully that makes sense. And also, we're about to jump in, but I want to make sure the purpose of this Bootup is not really for us to learn C++ entirely. That's not even possible for 5 hours, let alone 2 hours here. The purpose here is to show you what's out there. With C++, it comes with a lot of moving parts. With Java, it's relatively easy, right? You have the source code, you compile it, and for Java, it has this model of write once, run everywhere. So at least that's their design goal, which means if you have the source code, you can basically just write it and compile it. Compile means you turn that into a sort of a binary, and the binary is for machine to understand. Once you have that binary, once you have converted to the machine code, the quote unquote the machine code, then whether it's Windows or Mac or even Linux, it's the same. There's no additional work for you to do. With C++, it's lower level, and the downside coming from it is that for each platform, for Windows, Mac, for different processors, very likely you're gonna have to compile that differently. You have different compiler for different system. So what that means is just that there are a lot of moving parts when dealing with C++. So the goal today is really just to show you some options. For example, even just compiling C++. You have, I'm going to show you three different ways. If you count the IDE from that you can use, for example, Visual Studio, there's four ways. So there are so many different ways. I'm going to show you real quickly. So at least you're aware of them. You don't necessarily have to use them. But the goal is at least we know and we are aware of all those options. Um, the same with the 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 C++ itself. The C++, the language has so much content in there. For example, even the memory address, the pointer part, there's smart pointer, there's a primitive pointer, and the for today we'll focus on the basic stuff. And the goal is at the end of the day, you will have the knowledge of the potent, like all the options of the tool, some of the options of the tools, I would say, and you can pick a few that work for your situation. Some people like this, some people like that. You can pick it based on the information you get from here, and you would just be able to start writing code. So that's the goal of this Bootup. Okay. Okay, so with that out of the way, there are three big parts of the talk today. The first part I call this a baby step. Baby step just means the basic stuff, right? With this, you should be able to write Hello World. You should be able to write some basic code using C++. So that's the first part. The second part is sort of a mini lecture about memory. The way I go about this is the there's a big part if you because we came from Python, we came from Java, the memory management is a big part for us. And the way we are going today is first we try to understand how the memory works before even understand the C++. What's out there with for example, if you put 64 gigabytes of memory into the system, then when you write code, you want to use them. How are those memory allocated and freed and all those things? So we have a general understanding of how memory system work. And after that, we will, based on that knowledge, all the discussion about the pointers reference should come to you pretty easily. So we understand knowledge first, and then we move on to the pointers from C++. So that's the second part. The third part is more about OOP, the object-oriented programming. That part would be relatively quick because it's pretty much the same concept comparing to from other languages like Java. So I will not spend too much time. I'm going to show you a few examples, and that should be it. And the key thing, I'll have a few focus there so that you know what to focus on. But other than that, it's pretty similar. So we won't spend too much time. So quick summary, we have the baby steps, then we move on to the memory system, and the last one would be the OOP. Okay. All right. The first one is baby steps. And as I said here, this is my view. With when working with things like C++ in 342, a big part of the battle or a big part of being successful in this kind of class, in this class, is you want to be friend, you want to be comfortable with the tools. As I said, there's so many different combination of tools. You can pick your set, but once you have your set, being proficient, being effective with the tools that you have chosen is very important. It's not uncommon. In my teaching of 342, even throughout the semesters, the student would keep struggling with how to use this, how to use that. In the IDE, by the end of the semester, they will start to realize, oh, I didn't know I could do that. For the debugging, oh, I didn't know I should the debug code this way. They're still doing it the old way. So I would say at the beginning of the semester, the part of the tools that you will use, the part that the professor use in the class, make sure you understand that and make sure you could do what they can do. It normally doesn't take much. If you take 20 minutes, just play with it. It's like learning how to ride a bicycle. Just spend some time every day and you won't be surprised after a week. Then you will be pretty good with all those tools. You'll be the expert for that part of the tool, and that's a big plus. That's going to help you tremendously throughout the semester. So this part you want to nail this part at the beginning. Okay, speaking of tools, this is roughly my summary of the relevant tools. So let me turn this into this mode. The first one is the IDE, and the Visual Studio series is normally the first choice. And for my teaching, I normally use C-Line. And we'll talk more about CLI in the next slide, but for IDE, there's normally two options. And the benefit of using IDE is they provide a very good debugging tools. So it's not really just for like autocomplete the color. If we are looking for just that, then you can use Vim. You can use some kind of editor. But the real benefit of using this kind of development tool is their debugger. Okay, the second one is Vergrind. Vergrind is called this a memory checker. This is the code when we have our code and we want to make sure the code does not have any memory leak. If you don't know what the memory leak, just real quickly, that's where you allocate some memory, you use it, but you forgot to return that when the code finishes. And that's normally a bad thing. It's normally bad when the code runs for a long time, a few months or years. And if your code just keep allocating memory, but they did not really properly return them, then you could end up with a situation where there's no more memory left. It's like you keep taking money from a bank or keep everybody is borrowing book from a library, but no one is returning them. You can imagine at the end, there will be no money left in the bank and there will be no book left in the bank and the system just crash. In this situation, if we borrow memory, if we use memory from the system, we need to return them. And the Vergrind is just to make sure that in our code, we are doing that. Third set is more of a source code control. I think you guys have had the session with the Git and the GitHub. Those are very, very, very important. In my class, I would use this a lot intensively. Um, uh, for this part, it actually goes beyond this class. As I said, C++, you don't necessarily use them in your career. It's really just a learning tool for us to understand the system. But the source code part, the Git and GitHub, will go beyond your career. We will go beyond your study here. Because it's widely used in the industry, whether you're in the software or in pretty much anywhere you're dealing with. If you're dealing with code, you will be using Git and GitHub. And so for this part, a different professor use this differently. I would suggest just take this chance and try to use as much as possible so that when you graduate, you already have this under your belt. If you want to be the expert of any of these four tools, you won't be the expert of Git and GitHub here. The last tools is Linux. I don't know how many people have good experience or have spent some time with Linux. The reason we want to use Linux here, you might have that question because you don't have Linux on your machine, I'm assuming. You have a laptop, probably a desktop, you're running Windows or Mac. Then why do we need Linux? Because if we can compile code and run code on Windows or Mac, why do we need the Ubuntu? Well, why do we need the Linux? The answer really is that as we said, there for each of those three platforms, Windows, Mac, and Linux, there will be different set of compiler. The code would behave differently, slightly differently. If you compile on Windows, it will not run on Linux. So the Linux environment is sort of a common environment. From what I know from what I do in my 342, normally when the students submit the homework, it doesn't matter what you use to write your code. The code you submit will be checked and verified and graded on a Linux machine. So we have the common machine, and so that it doesn't matter what the student use. in that case, you might ask, if that's the case, why can't we just use Windows or Mac? And that's a fair question. The answer to that question is on Ubuntu. For me, the answer to that question is really it has the best memory check tools. The Vergine, as far as I know, it runs on Ubuntu. I tried to figure this out how to run that on Mac, and I haven't tried it on Windows. But as far as I know, the easiest way to run the memory checker is on Linux. So that's why we normally use Linux for two reasons. One is sort of a standard environment where things can be checked. And the second reason is just for the memory checker, I would normally just use the Vagrant. Okay, so a bit more about the IDE. As I said, Visual Studio Code is pretty popular. The one I use is C-Line, and the reason I choose this is here. First of all, it runs on Mac and Windows. Second of all, it runs natively. By that, I mean you write the code in the C line. When you run the code, you don't need to use a Linux machine to run it or compile it. And it can compile and run the code right on your system, right on your Mac or Windows. The third is that as a student, you do get a free license at least for a year. You can also extend that for free. It's an educational license as long as you have the UW email. And with that license, it comes with many other fantastic tools like IntelliJ for Java, PyCharm for Python, so on and so forth. I use their tools a lot in my own work. So that's a good benefit of having those things. And the last but not least is that it's free for students. It doesn't cost you anything. And from the industry, as far as I know, if you're writing Java, IntelliJ here is pretty much the standard. So it's a good to have. And it makes things a lot easier. From some feedback in my last class, the student were saying that with Visual Studio 2, they have to set up a lot of things with Docker or the connected to just from their development for their local development environment. They have to have Visual Studio Code set up together with other system, being a standalone Linux machine from the school lab, or they need to run Docker somewhere, and the Docker is essentially it has Linux running in it, and basically you have to have two operating systems together to do one thing. And with C-Line, you just need to have this one, and you can do everything just right on it. As I said, debugging is or the debugging tools from those IDEs are very, very powerful and useful. So the one thing from learning C++, or even in the 143, I would say this too, that we should learn to use this so that you should never be guessing what the code is doing. What that means is if you write code, you run it, or you are trying to figure out whether the code is doing what you think it's doing or the test is failing. When those things happen, you need to inspect the code a bit closer. And the way to do that is, for one, you have to read the code. But if, for instance, for some piece of the code, you need to understand what those variables are, what's the value. You should never be guessing, and you should not be using print to check those values. And the proper way is just the system already, the IDE already provide all these tools, and you should use all these things like breakpoint, step in, step over to read the variables, understand the code, and it's a lot faster and more accurate than trying to guess what the code has. Okay, so much about IDE. The next topic is still in the tooling part. It's about the Linux. If you don't have much experience with Linux, I would suggest you definitely spend some time and take this as a learning opportunity to learn another operating system. It's pretty cool. It's used a lot. And for example, for my work at Amazon AWS, I used to be a software engineer at Amazon. Pretty much the backend server are all running some version of Linux, and it has its own tooling system, its own so-called ecosystem of tools. So it takes a while. It took me quite a few years to get comfortable with all the tools. So the earlier you start, the more time you have to learn those and get better at them. So take this as a learning opportunity. And because we need to run Vagrant for memory check on Ubuntu, on Linux, and I would say just I use the word pet a Linux system. Just find a Linux machine that you can use anytime at your finger. There are normally two options. First option is that you can get a machine from the school. There's a school machine from the lab. And the second option is you could use the cloud computing machine. So here I want to show you real quickly. The one you do is you search Amazon AWS, and the AWS stands for Amazon Web Service. This is just a cloud, and the cloud is nothing but a bunch of machine in somewhere that you could borrow, and you're charged for the time you borrow. In this case, we are gonna use this free tier, so there's no cost because we're gonna use pretty small machine. Um, And what we want from this part is just to create a Linux machine in the cloud, connect to it. It becomes your machine forever, and you got enough hours throughout the years that there's no charge for you. So I'm going to show you real quickly the beginning part of this process. So go to AWS, create your account. I already have a Mac account, so I'm going to use that. And inside this, you can just search EC2. This is the place, this is a service where you could create your own machine. And the machine in the cloud, the term is called instance. An instance is just a machine. We call this a virtual machine, but still, it's a machine. It's a machine that's running Linux on it. You go through the launch instance, and we're going to use Ubuntu. Select that. And because we want to use the free tier, you're going to use the free tier eligible T2 micro. This is just saying one CPU, 1 gig of memory, so on and so forth. The charge here does not apply to you because it's free. And just follow this process, and you should be able to create a machine. If you're stuck, just just go on YouTube or use ChatGPT, and there's hundreds of videos about how to create a machine. The key thing is you want to create a machine with the Linux Ubuntu. There are different versions of Linux. You want to use Ubuntu. It's probably the easiest to install software, manage, and use. There's some slight difference between all these different versions of Linux. But other than that, select Ubuntu, select this part, you don't really change this, and make sure you select the free tier. And the rest would be just follow those steps. And this part is saying how much storage you should have in this machine. Um, for our purpose, 8 gig is more than enough. So you don't have to increase it. And I'm pretty sure if you increase, or actually it says here, so you can increase this to 30. But I don't think it's necessary. Once you have the machine, you can use it, and you're going to use the tools. If you're on Mac, you're going to use SSH into um, is yeah, you're going to use SSH. This is how it looks like. So if I go to a different window and do SSH, um, this is the IP address you get from the machine. You're going to get a key. And if you do this, and all of a sudden you're in this machine. And now we're in the Linux, then you could do all the normal Linux thing, right? Okay, so speaking of the cloud machine, AWS from Amazon is one option. Google has Google Cloud, which also give you, if I remember correctly, it's like $300 free credit. And from Microsoft, there's Azure. So those are the three big cloud computing option where you could get a machine that runs Linux, so you don't have to build your own machine. Um, as I said, this is one of the option. It could be in the cloud. You could also, if you don't want to bother with the cloud, the school already has pretty good machines. You could also use that. Okay, let's see. The memory check, we're gonna do this when we talk about the memory. So just skip this part for now. Now let's do the baby step. The baby step basics here is really about compiling. And this is the key thing. For a code, whether you write it in Python, Java, or C++, there are two essential parts. One is the source code, and the other one is so-called machine code. And the source code is what we use, what we write. As a human, this is what we write. The machine code is we use this thing called compiler, and the compiler, the job of the compiler is to take the source code and convert that into a big blob of zero and ones, and those are the instructions in zero and ones that the machine could understand, the machine could run. So when we're actually running our code, we're not running the text file, we're running the compiled or the machine code. We call this executable or binary, and that's what CPU understands. The key thing, the one interesting here is I put for this icon, I purposely select the icon of a few people. This is to say that the source code we write is normally not just for ourselves to understand. It's for other people to read. It's for the future you to read. So it's important. The source code is really for human to understand and to read. So it's important for us to learn how to write humanly readable code or human-friendly code, so that your colleague does not when your colleagues read your code, they don't hate you, or in a few months when you come back and read your own code, you don't hate yourself. So yeah, the source code, the key mindset is for human to read. And just real quickly, I want to mention this. If you want to learn more about how to write humanly readable code, a good starting point is this book called Clean Code. This for any CS major or people writing code or people writing code for a project that involve like more than one people, especially, you want to get a copy of this book and read about it. Okay. So that's a little bit off the topic on the source code. And speaking of compiling, I put a different kind of CPU here because the machine code in terms of C++ is machine specific, which means it's not just one compiler anymore. For example, Intel CPU will have a compiler, and for Mac, you have a different compiler. The compiler is just some program that people have written to turn the source code into the binary. A very interesting question, if you want to think about it, is that if the compiler's job is to convert source code into the machine code, what was compiler written into? Like when people write the compiler code, what did they use to compile the compiler code into binary so the compiler binary can turn our source code into the machine code? That's a very good thing to use ChatGPT for. So if at night if you can't fall asleep, that's a good rabbit hole to come down and do a bit of research with ChatGPT. Okay. With this part, now we understand we have the source code, we have the machine code, and the next general question is like how does it work in action? So I want to show you real quickly that part. So for that, I'm gonna go into this Linux machine. I have this machine from AWS, so I'm gonna, for example, create a quick folder. I'm gonna go to the temp, create a quick folder called the 342 demo, and from here, let me see if I have that. I don't have that, so I'm gonna go to the my repository, and I'll get the -v. This is the repository that has this code. I'll just copy the link, go to the Linux machine and clone it. It's there. And let's go to 342 demo. Actually, that was wrong. It should be in the 342 demo. And let me just clone this again. Okay, so we have this here, and it's hard to see, so I'm gonna okay, so now we have the color, which is good. We have 4 folders here. Those are just 4 steps. So let's go into the first one. Those are 3 different ways of compiling your source code into binary. So here is where I'm going to show you the options, just so you know it's there. First one is we have this source code. Make this larger. The code is pretty straightforward. Also treat this as our first formal introduction to the C++ code. Try to read it. If you had done plenty of Java before, this shouldn't be too hard for you to read. You should be able to guess what this is. This is a main function. A main function is where the code starts. This is sort of an array, and we have an array of 5 elements. This is a for loop. We can go through this, and here is where for each element, we're gonna time 2 of each element. So if we are starting with 1, 2, 3, 4, 5, after this step, it should be 2, 4, 6, 8, and 10. Okay, and we're gonna print it out. So that's pretty much the code. The include is similar to the import in Java. We are using some library. In this case, the printf comes from this library. Okay. Here I want to pause real quickly and ask you another question. What other difference that you can imagine or you could see comparing this code with Java? If you were to write the same code in Java, what difference do you see here? And the key difference that I can think of is in Java, everything is part of a class. Even if you just have just one main function, you still have to have the put that into a class, right? In C++, there's no such limitation, partially because that C++ is sort of something that evolved out of C, the C language, and the C has no class. C is not OOP, so there's no class there. Like everything, the closest thing in C that's to the concept of class is struct. A struct is just a class without the functions, without the member functions. But still, conceptually, in C, there's no class, and C++ sort of inherited that you don't necessarily have to have a class, but you can. Okay. Okay, so this is a source code. As we said, this is for human to digest, to understand. How do we turn this into the binary? In this file, I have a cheat sheet here. Basically, remember the 3 parts. We have the source code, we have compiler, and we have the machine code. Now we have the source code. The source code is this, and if I show here, this is this. On Linux, you can use file to see hello world. You see that it's a text file. Okay, then where's the compiler? The compiler on Linux is called the G++. And on Linux, you can also use the menu. The menu show you the full information of what this is, and you can see there's just so many options that you can use. In our case, just to make things easier, you could just use the compiler. We give compiler the source code, and we tell it just create the executable or the binary. We call this exe. Let's call it just a hello world. But in this case, with Windows, you have to do exe because that's what the Windows use to know, oh, this is an executable. For Linux, we can have any name. We don't even have to have extension, or you can even have dog. It doesn't matter. In this case, we will not have anything. So now if we do this, you see that in the green color, this is the produced executable. So if I use this to see the type of this file, you could see that it's executable. Okay, how do we run this? Then on this machine, we do this. This means the current folder and the tab. Then we get this file name and we run it, and we see 2, 4, 6, 8, and 10. So that's the result of this code. Okay. So this is the basic, the easiest way to turn the source code into a binary. The next step is basically saying for one file, it's okay, but we could end up with a situation like this where there's multiple files and only one of them is the main, right? If we go to this one, we could see that um, and by the way, some of this, if you don't understand, don't worry, we're going to get to them. But for this part, we have this main function. The main function is having this, is referring or is using this class called cat. As you can see, it's taking code from the cat.h. And just to show you, we can see what's in the cat.h. So here on top of there, here is a cat.h. As you can see, it's just a class. Okay, but it's not in this file, and we end up with a situation where we have multiple files. If we do the same thing with this, let's call this, actually, if you don't do anything, it's going to produce with a default name. But because in the main file, it's going to use the cat, and the cat is going to use some other file, then we cannot just compile this one file with just a G++. It doesn't work because this is just one file. It's part of the source code. It doesn't have all the source code. So how do we deal with this? We need all the source code so that the executable can be built, right? If there's some part of the code that's missing, then how are we supposed to create an executable? The code cannot execute. The way to do that, or one way to do that is the tool called a makefile. Let me just do a quick search. Makefile. Yeah, sometimes it's called a make. So if I do menu make, does it? Yeah. So this thing is called a make, and the configuration file it uses is called a makefile. What that does is sort of a dependency management tool. And for C++, for example, with this project, this is sort of how it works. It starts from this part, and to run this, we simply just type make, and it will look for a file called a makefile in its current folder. And if we do that, you see that it's compiling the first source code, and it's generating a .o. A .o is sort of a half compiled code. And it's doing that for the first three. So it compiled the main.cpp. CPP is just another source code. For example, cat.cpp looks like this. The pet.cpp looks like this. But nevertheless, we have three CPP files. And the compiling process is saying that we need to compile all three. And then we need to put them all together into the final executable. This way, we have all the source code we need for this to run, but we cannot just say do what. In fact, if you want to, you could, I think, you could do main.cpp, pet.cpp, and pet.cpp. I think it potentially will work. Yeah, it will still work. For example, this still works. But for any project that has more than 4 files, it gets complicated. And using makefile is a way for us to say, hey, I need to compile this project. The final executable would be called this. This is a variable. And start from all. So this part, you can read this as sort of a tree structure, and the tree represents the dependency of files. What I mean by that is when we try to compile this, it will say, okay, for this is called the exe, right? For this one, we need a 3.0. And for this first dot O, we're gonna in this column, we're gonna look for, okay, that says main.o. So this part is how we can get the main dot. Remember, we started with main.cpp. And by compiling the main.cpp into main.o, we have the main.o. So now we have the first one. Then how do we get the second one? cat.o. Okay, we come here. This says cat.o colon. This tells us to get this, we need these two files. And once we have these two files, we're going to run this command and we're going to get cat.o. This command is uh, what we saw here. We compare that to this. This is a variable. This is just a variable for G++. This is a flag, sort of a configuration. Just ignore this for now. And so we have G++, we have the flag. We use the source code file and produce this cat.o. So now we have the second one. Similarly, the third one, pad.o, where do we have pad.o here? This says to generate this file, we need these two files. And once we have these two files, we run this command, which is just GCC, so on and so forth, and we can produce this. Once we have all three of this, then we're going to run this command, which is essentially just take the 3.0 file and produce the final executable. So this is at the top of the tree, and the tree has three branches. If you imagine this from top down, we have the top node, we have three more nodes. For each of this, it has, for example, the main has one branch. For cat.o, it has two branches, and for pad.o, it has three branches. So if you think of it that way, Makefile is nothing but just a dependency management tool. It allows us to represent this kind of dependency between files. If you have this two file, you can do one thing. If you have the other two files, you can do another thing. Once you have these two intermediate files, you can do more things. To give you another example, actually, if we take away all those C++ concept, if we just go in there and use Makefile to say, hey, I need to have, for my morning routine, I'll show you the example. For my morning routine, I have all these things I need to do before I can get in the car and drive for school. I need to finish all of them. I need to make sure that by the time I leave home, I have not forgotten any of these steps. But for all those steps, there's a sequence in there. I can't just do them randomly. I cannot just pick one at a random time. For example, the process is to leave home for work. I need to do two things. One is I have to have breakfast. The other one is I need to get in the car. For breakfast, I need to cook the eggs and then make coffee before I could have my breakfast. And get in the car, to be able to do that, I need to first put the laptop in the backpack and find the car key. I need to have both of them there so I could get in the car. And for me to leave home for work, I need to have both had the breakfast and I'm already in the car. And only after those two steps are done, I will be able to leave home. So you see that this is kind of a dependency. And if you remember from the 143 discussion, if tree traverse was discussed there, this is essentially the post order traverse of this tree. But the interesting part is we could use Makefile to say this tree structure is good for storing data, but it's hard for a human to follow, right? Where do I start? There's four things I could start with. For human, it's easier if you just have a list, right? The first step, second step, I will just follow those. The way the steps are created, it will guarantee that any of these dependencies is not violated. It will still follow the dependency, but I'm not forgetting any step. So for human, it's easier to follow a like a one dimension step, and that we could use this makefile and we could express the dependency in the makefile because if you remember, a makefile is nothing just to say to do this, I need to do the two things, and to have breakfast, I need to let's see, where's breakfast? Yeah, for breakfast, I need to cook eggs and make coffee. For cook egg, I need to here is just print it out and make coffee. I need to do this. Once I'm done with breakfast, I need to start driving. But for start driving, I have two more things to do. And for the first thing, we do something. For putting the laptop in the backpack, we need to do this. Okay. Um, so having this make file, if I just run it, we have the steps. We have the step in a way that this is, if you read through this cook egg, make coffee, then we can have breakfast and find the car key. And we put the laptop in the backpack and put the charger in the backpack. And then we put the laptop in the backpack. And then we could, once we have this part and once we have this part, then we could start driving. So this is this is exactly the post order traverse of this tree if you're talking about the data structure. But essentially, we have this dependency, and because the makefile can represent it, it's nothing but just a dependency expression tool in a way. Then we could just express the dependency in this way and just ask it to run it, and it will follow the dependency and give you all the result. Okay. So for this part, there's no C++, but it does show you what's this makefile for. And the way we use makefile is to say, let me show you this one more time. Makefile. Because the way we compile code, there's naturally some sort of a dependency tree there, and we're just using makefile to express that dependency tree. We need to compile this file first. We need to compile that file second, and then we put them together. Then we do something else. So we express that in the makefile, and once we run that, makefile would follow the dependency, would respect the correct sequence, and just do things in the sequence so that we could get this executable at the end. Okay, so that's the second one. The problem with makefile is this. The problem with makefile is that because for each platform, for Windows, Mac, or Linux, the makefile would have to be different, and it will have to be different in a way that it's really just the compiler and its flags are different because the source code is the same. It doesn't matter what operating system you have, we'll still have the same source code. It's just text. But on different system, the compiler would be different. For example, if I go to my Mac, the C++ compiler is called this. So as you can see, this is the C++. Actually, it's also the Objective C because this is on the Mac. This is what the compiler called. The compiler is called. It's C language plus plus. This is on Mac, and here on the Linux machine is called G plus plus. And if you wonder where the name come from, is called GNU Project C and C++ compiler. So the first G comes from this. But nonetheless, on this machine, it's called the G++. And on Windows, I don't even know, I don't even remember what that's called. So if we have different operating system, the makefile would have to be different. And for us human, we know the compiling dependency is the same. It's still doing, we have this two file, compile them, put them together. We have the other two file. So the sequence there is still the same, but it's just the tool we use to compile them are different. And if human have to, if we have to write all those, it gets a bit tedious. So to solve that, the third option is, or a higher level option is called the CMake. Um, CMake is a tool where it can write the compiler, it can write the makefile for you. So if we have three different systems, then we don't have, as a human, we don't have to maintain three different versions. We just write something like this. This extracted or abstracted away a lot of the details. For example, here you don't see the compiler, and you don't really see the flags. Here we can say this flag, but what we do see is just a file. And what this really says is we have all these files. I'm going to use the compiler, and the final result of the executable is going to call by the project name, which is just this. And so what this can do is, let me show you. In this file, in this folder, we have all these files, which is the same as in the previous project. But we don't have the makefile here. And the way to create a makefile is, let's just make things easier to see. I'm going to create a folder and go to the folder, and I'm going to use cmake dot dot. The two dots here represents the cmake list.txt in the folder above my current folder. Remember, I went into this folder from here. So if I do this, and you see that it does something, and all of a sudden we have makefiles. The first letter, uppercase, lowercase, doesn't really matter, but the makefile, if you look at this, it has more stuff, but it's pretty much still the same thing. And the way we use this, once we have the makefile, then the rest of the step would be the same. We do make, and you can see that it's building the 3-1, right? If I scroll early enough, let me see if I can find it. It's doing the same thing. Probably not there. So let me show you something cool. We could go to the upper level. CPP and make. Yeah, this is using the makefile that we write. This is using the makefile that's created by CMake and if you compare, there's 4 lines: man, cat, pet, and the final executable: man, cat, pet, executable. So it's pretty much the same. If I go back to here, so what CMake does is really just so that we don't have to write the same makefile with only the difference is the compiler name, and it can create this on Windows, on Windows or on Mac. The same makefile will still work. On Mac, it will create a makefile for the Mac with the Mac compiler clang++. On Windows, it will create that. CMake is actually what I use in CLine. Remember, CLine is the IDE. But I would have a project that the CLine would be able to recognize this CMake file, and it can work with that. That's actually how CLine was able to work with the same project both on Windows and on Mac. Okay, it's not because CLine itself. It's really just because CLine is able to recognize CMake and use CMake, and CMake is the one that could create a different makefile both for Windows and for Mac with the same input. Okay, just real quickly, let's see this. It gives the same result. Okay, so as a quick summary, what we just saw is 3 different ways of compiling code. The first one is pretty straightforward. Start from the source code, and we just use the compiler. Once there's more than one, or there's too many files, we can just use the compiler manually. So we can use the makefile, and what the makefile provides us is to express the dependency between different files. And when we run the makefile, it will follow the dependency and compile and produce the executable. Problem with makefile is that it's sort of platform dependent. If we have different platform, even for the same set of source code, we have to write the different makefile. To not have to do that, then we can use CMake, we just have write one text sort of a configuration, and CMake could produce the makefile depending on what system you're on. And once we have the makefile for that system, for that operating system, then we could just use that to compile the code. So those are the three compiling. And if I get back here, yeah, all those things we just saw is really just for this slide. We have the source code, we have the compiler, and we use the compiler to create the machine code that the machine can run. I'm pretty sure you can already see that. Now we have three options, and a different professor would use different tools. You might use the compiler at the beginning, then they might move on to the makefile. And in my class, I would eventually use CMake. So at this time, it's really what the professor asks you to do and what you want to do. Um, okay. All right. So that's that. And at this time, I'm going to move on to some of the coding part. This is really just a quick coding demo of some semantics, C++ basic semantics. Um, so let me exit. Actually, I'm going to stay there. And I'm going to open up. This is on my Mac, by the way. And I'm going to go back to Bootup Playground. I have this project. Let me see. I probably have something there. I'm gonna reset. Okay, and I'll open this in C. It's a lot easier to write code here. Okay. In the next about 15 minutes, we're gonna simply just write some basic C++ code. Uh, First thing first is C++, the file name is not strictly defined, which and by that I mean comparing to Java, in Java, the file name has to match the class name in it, right? If you have a class called cat, then the file name has to be cat.java. In C++, there's no such requirement. You can have the file name can be anything. The convention is that it's called the CPP, C++. .cpp is the main body of the file. And sometimes you could also see people have like .h file. And in this case, so let's try that. And I'll create another one. Let's do here. Is the .h, sometimes it's called the .hpp. It's really just a header file. And I can have any name, so I'll just use the same main.h. I'll get rid of this. This is just something produced by the IDE. Actually, it should not be in that folder, so I'll drag this into this folder. So we have this main. The way we use this is sometimes, for example, this kind of include, remember include is just import. We're using someone else's code. We could put this code into our own .h, and we could include this. So in this case, I'll just include main.h. Come back here, it's still good. And in C++, you could do a cool thing called a pound. We call this pound define. Define is sort of a templated function, or just the, for example, 10. So that's a string. And the way this works is when the compiler compile this code into the binary, into the executable, whenever it sees TEN uppercase, it will just replace that with number 10. So for example, in here, if we want to print out this hello world 10 times, I would simply do 10. And if we put this back in here, and if we run this code, you could see that it's actually running 10 times. So when this code is compiled, the compiler would see this is 3-character TEN, and it will just go ahead and replace whatever this is. And by that, I mean, if you put the 10x here, the compiler would try to compile this into 10x. And so if I try to run it, you can see that it does not know. It's going to tell you invalid suffix on this. But remember, when the compiler compile code, there's no T in anymore. It will just see this. It will just, for essentially the code, when the compiler sees it, it will become this. And because there's an X, it doesn't really understand. That's not a legal statement for, or that's not a valid statement for C++. So that's why the compiling is failing. Um, and to fix that, we just need this part to be valid, and we can come back and run this. Okay. For this part, some basics. The main function is still the entry point of any function of your program, so that it doesn't matter what function you have. Then if you have a main function, that's where the code starts running. Speaking of that, let's have another function called the function one. And you could call that function one from the code. So if we put this part into the function one, and if we just put call function one, and it should run, right? Well, it's not. It's showing red. Why is this red? This is the part where I personally don't quite understand why C++ is not able to figure this out. I mean, it's 2024, and the problem here is that the function one is defined here and is defined after or below this main function. When the compiler compile this, it can only see what's above the current main function, and there's no function one above main. Remember, it's defined below this main function, and that's why it doesn't recognize this. For me, that statement doesn't make sense, because as human, we could see this is in the same file. Why can it not find this, right? And for this, unfortunately, there's no way to get around it. For this to work, we simply just have to define the function before the main. Here is simply we call this is not really defined, it's a declaration of function one. If I fix the typo. When we have this, then the compiler compile this, it sees this, it already sees, okay, there is a function one function somewhere, so I would not complain about this. I would trust that we do have this function body. We call this this is where function one is implemented. So we say this is the body of the function, and when the compiler sees this, it will trust the statement from this line 3 that the function body is somewhere in this function or somewhere in this file. Okay. And if we run this again, it's just as same as before, except now we are calling this function in here. So that's that. And a few more things, basics. We should know there's a variables. So let's call this variable equals 10. Those are basics, pretty much the same with converting to Java. And we can have array 5 equals 1, 2, 3, 4, 5. For this part, it confused people a little bit, especially when I'm teaching this in person. The bracket 0, bracket 1, those are not things I typed. Those are just the IDE's prompt. Just remind us. So for example, if I type this again, I'll type 1, comma, 2, comma, 3. And you can see the 0, 1, and 2 those are indexes. And by the way, in case you didn't notice, the array in C++ is the same as Java. A few constraints. Array is just a bunch of elements in the same concept, in the same construct, if you will. The requirement is that they are the same type, right? In this array, type is int. We could change this to float, and pretty much the same. and uh, and also array has a size. So in this case, we have 5 elements. So we could only put 5 things in it. 1, 2, 3, 4, 5. And speaking of number of elements, uh, array in C++ is zero based. So the index, the first one start from zero. Um, so that's that. Um, okay, so those are the pretty much the basics. But before we move on, I want to do a simple. Let's try something to solve a simple problem. And the problem we are trying to solve is just a search in an array. And to make things easier to understand, to make it easy to search, let's assume this array, all the data in there are sorted. And what I mean by that is, for instance, if we have 5 elements, let's call those 2, 4, 6, 13, and 24, right? We have 5 elements. And also just have it as integer. Let's say we are looking for a certain value. Let's call that target, and let's call that, let's pick 113, okay? And at this point, we want to write a search function. And the search function is going to tell us, so the search function is going to return something. And that the return value will tell us if 13 or if the target is found inside this array. It's going to tell us what's the index. So it's going to return integer because the index is an integer. And for that purpose, we also need to pass in this array. Uh, okay. And I'll put a function here. Similar to before, because search function is defined after the main, we need to put it before it, and we can have this here. Okay. Okay. So how do we do the search? Inside the main function, we can simply say index equals search array and target. And after that, we'll print out the array. Speaking of printing, there are 2 main ways of print things. The printf sort of inherited from C, from the C language. So you could do %d, this. The %d here means this is integer. If this is, for example, a floating point number, you could do %f. If this is a character like A, B, or C, you could do this. So here is sort of a type indicator of what this is. The C++ way is like this: IDX standard out NDL. It does the same thing. The benefit, I guess, here is we don't have to specify what type this is. So there's no type. All we care about is the index value or the value in this index variable. And we just put a variable here and it will just print it out. For this demo, I'll just use this one. Okay. Um, okay, for this part, how do we do the search? Well, we have an array of data, right? So the search is to say, do we have this target in this array? There could be duplicates, right? There could be more than one target value in this, but nevertheless, if we can find one, that's good enough. Um, with that, if this is an array, then we need to have a way to go through each element. And the way to do that is we simply go have a loop, and the loop would go through this entire array. And now we have a problem. What would it be here? What would be the size of this array? In Java, you could do length, I think, if I remember correctly. Apparently, you cannot do it here. It says array this has, it doesn't know what this means. That's more of a Java thing. For C++, we cannot do that. And in fact, in C++, the array, just from this part, we don't know what's the size. For this part, there's a trick you could do to, for example, if the array is defined this way, there's a trick you could do to get the size. But if sometimes the array is not defined this way, we haven't talked about pointer yet, but it could be defined in this way. It still works, and that trick would not work. The solution is, well, we just have to pass in the length. We just have to tell the search function how many elements are there. So now this part become this. And the array part, I think we need to do this. Okay. And for the search, then it's pretty straightforward. The I would go from the beginning to the end, 1+1. So go from 0, 1, 2, 3, 4 until we find something. And the way we say a certain index or the element or the value at a certain index of the array is similar to Java. We just put a bracket. And if this is the same as the target, we simply return. What do we return? We should return the index. Okay. If we go through this loop and we never hit this never happens, then we know that we didn't find anything. Then if the target is not found in this array, we simply return -1. This is what we called a linear search. Okay. Okay, the code is there. Let's run this. And let me see. Oh, here is just saying that because we added the file, it doesn't know that part. So let me do that and reload the CMake project, see if that helped. It doesn't really. To make things simpler, I'll just put this back. Actually, let's take a look at this. Search reference from, okay. Now, actually, it's not related to this. So let's try to fix this. Search target. Oh, I see the reason. It's a surprising the IDE did not tell us. The declaration before the main function has 2 parameters. Oh, here we have 3. That's not going to work. So we need to add one so they match. Int length. In this part, we need to do, we have 5 elements. All of a sudden, we are calling the right function now. Let's try to run this again. Worked. And the return value is 3. Why is it 3? And should it be 3? Target 13, we're looking for 13 in here. 13 is the third element. You can see that index 3. So returning 3 seems correct. So let's try to search something else. If we search 99, and it's returning -1, so it tells us the code is correct. Okay. Okay, so far so good. The code is correct based on the 2 test cases, and the search is done. Another thing in C++ that you need to learn eventually is the complexity. And if you remember from 143, the big O of this function is what? The time complexity, let's call this a time complexity for this function is O of n, right? Because the worst case scenario, how many elements do we have to visit to find a target? And the worst case scenario is the target we're looking for is the last one. And if there's n elements in this array, the number of comparisons we have to do here is n, right? If n is 5 in this case, then the worst case, we need to compare 5 or 4 times. If n is 200, then the worst case, for 5, we need to compare 5 times. If the array has 200 elements, then the worst case scenario, we have to compare 200 times. If the array has 5,000, then we have to compare 5,000. So the size of the array would be related to the number of time we have to compare. So that shows how much effort or how many steps do we have to iterate before we could find the result in the worst case scenario. Just to make this a bit interesting, to improve the complexity, we could simply do a binary search. And the binary search, if you have not done it before, is the idea that so instead of searching from the beginning to the end, is this it? Is this it? Is this it? If we ask every single element instead of doing that, what we do is we start from the middle because it's sorted, right? In this example, we are searching 14. If we start in the middle, it's 9, and we know 14 is larger than 9. So the 14, if we do have 14 in this array, because this is 9, it cannot be on the left side because everything on the left side is smaller than 9 and is smaller than 14. So 14 cannot be here. So the next iteration, we're going to start from the right side. And with the right side, we also jump to the middle of the right side, which is 12. And we compare 14 with 12. 12 is smaller than 14. Then we know that 14 cannot be on the left side of 12. So the next iteration, we're going to go to the right side of 12. And eventually, we're going to find 14. This is kind of binary search. So let's just implement this real quickly. And we'll talk about the complexity real quickly before we move on to the next section. Okay, so binary search, how do we do that? Well, in this case, we're not really starting from the beginning. We're starting from the middle. And as you can see, every iteration, the search range would be different. So we need something to represent the range. And for the range, we're going to have a start index, and we're going to have an end index. And so that would mark the range of the search. At the beginning, the start index would be from 0, and the end index would be length. Okay. Then the step is we go to the middle, we compare. And there's some kind of loop would be involved. We're going to delay that part. And the step is that we need an index for the middle. So we're going to have a mid index equals to get the middle one, remember this is 0, this is n minus 1. The one in the middle is the start index plus the end index divided by 2. For example, if it is 5, 0 plus 5, that's 5, 5 divided by 2. Because the integer is going to be 2, so it's going to be 6, right? 6 is going to be the one in the middle, which is correct here. Okay, and from this array, if the element in the middle is the target, then similar to the linear search, we're going to return the mid index. Otherwise, if the target is on the right side, if this is on the right side, what do we do? Well, if it's on the right side, then we should not search on the left side. So the search window would be only the right side. And to change the window, the window currently is at the beginning and end. If we're changing to the right side, the end should not change. And we're only changing where it starts. So the start index would be what? The start index would be the mid index plus 1. Otherwise, in the otherwise case, it will be saying that the target, for example, if we're looking for 3, 3 is smaller than 9, so the search window is going to be updated to the left side. And for the left side, the starting index should not change. We only need to update the end index. And for that, we'll say end index equals the mid index minus 1. And this part would just be updating the window. And then we'll go back to the iteration. We'll do the next iteration and so on and so forth. If we found something, then it's going to return from here. if the entire loop is done, we still didn't find anything, then we simply just return -1. Okay. The last thing that we need to figure out is when does the loop stop? The loop has to stop somewhere. So when does it stop? A simple way to look at this is just look at the window, right? The window is marked by the start index and the end index. And at some point, we're either moving the start index to the right or we're moving the end index to the left. At some point, they're going to run into each other, but still, as long as the start index is equal to or larger than the end index, which means the start index is on the left side or on the same location as the end index. If that's the case, there's still some data to search, then we should do this. Otherwise, we should stop. Okay, so with this, we change a few things. So let's change just make this calling the right function. And for this part, we're gonna have this happy, and let's run this. Searching 99, still return -1 because we don't have 99 here. Search 13, and it's still returning -1. It should return 3, right? Okay, so that gives us a chance to do some debugging of this. Uh, why is this returning -1? Okay, the way, as we said at the beginning, we are going into we're using the IDE, and one of the benefit of using IDE is the debugging tools. And the debugging tool to start with, we should use this thing called a breakpoint. The breakpoint is something that allow us to pause the running of the program. And when the program execution is paused, we get a chance to see what's the variable. So here we're going to use that as a demo, and we want to run this. But when we run this binary search, we know something is wrong there. The way to do that is we don't want the code to run through. We simply want the code to stop right here. And we're going to do them one step at a time and see where things are going. Okay. So for that to work, we cannot use this run. We should use the debug. And let's see here. Okay. Okay. So it ran, stopped, paused right on the blue line. And we have 0 and 5, which is the input. We can see the value here too, right? Okay, so because it stopped here, we have two options. One is called a step over. So basically, we go one step. The other option is step into. Step into is really used if this is a function, we can step inside that function. For this case, it's just one statement. So we're going to step over. And as we can see, it immediately jumped to return to -1. When we're searching 13, it shouldn't, right? It should go inside here. So why is that the case? Oh, I see. So as you can see here, the logic is sort of inversed. That's the mistake, right? So if we stop this, take this away, the loop should be running as long as the start index is lower or equal to the end index. So if we change this to this, then this part sort of makes sense, right? If we run this again, and now we get 3. Okay, so that I did not plan that part. It's just a mistake on my part, on my side. But as you can see, if the code is not doing what you think it should be doing, what we should not be doing. If that in that situation, you should not do is just stare at the code and trying to figure out what's wrong. By having a breakpoint here, we know that it went from this line directly to this line. We know this part was not running. Okay, why is it not running? If it's not running, that means this part has something missed. Oh, that's the issue. So as you can see, process is sort of like detective work, right? You find some clue, and for the situation in that clue to be true, what else has to be true? Then you just peel the onion, going backward, and eventually you'll be able to find it. Using breakpoint, using all those debugging tools from whether it's a C line or Visual Studio Code, it's going to be super easy to do that instead of just staring at the code. Okay, so this is binary search. My last question for this part is then if this is the linear search has the big O of n, what would be the time complexity in terms of big O for this binary search? Um, the way binary search work is essentially every time we're gonna like every iteration we will remove half of the data from the search, right? In this case, start from the middle. If we search 14, the first half of this array will never consider them again. That's essentially every step, every iteration, we cut the search things, cut the amount of data to search in half. And by that, you could do the math, but that become log n. To give you some simple example, if we have 200 elements, let me use the calculator. If you have 200 elements, with the linear search, the complexity is O(n), right? So the worst case, we have to compare 200 times. With the binary search, how many times in the worst case scenario do we have to compare? And to answer that, that's essentially the question, how many times can we divide 200 by 2, right? So if we do divided by 2, that's 1 time, 2 time, 3 time, 4 time, 5 times, 6 time, 7 time, and 8 time. So it's about 7 to 8 times. That's a big improvement, if you ask me, right? Going from worst case 200 times to 7 times. And the 7 time is guaranteed. It guarantee you it's not going to be anything above 7 or 8. So it's sort of give you the worst case scenario, and the worst case scenario for binary search is a lot better than just a simple linear search. This is something that every time you write code in 342, you have to consider this. Um, and a common mistake that I see from student writing homework in 342 is they are aware of this fact that they need to consider complexity, but that sort of limiting or essentially preventing them from writing the code. The step I would recommend is write something that works and then make it faster, and then make it efficient. Do not try to write the perfect code on the first try. Write something, even though the performance in our case, we wrote we wrote the linear search, right? Performance sucks in that one. Yes, but we have something running. We know it's correct. And once we have that, then we can think, okay, now it's time to make this faster. Now that we have this one work, it tells us the correct result. It's just not fast enough. Then how do we make this faster? And the way to do that is, uh, in our case, when we find out, okay, binary search, we don't have to search every single element. Because the array is sorted, we could do binary search and we write the binary search code. It's producing the same result with the linear search, but as we saw in the time complexity, it went from 200 times comparison to just 7 or 8 times in this case. Okay, so for this part, this is the end of this session. With this, I hope it gave you a good understanding of or a good idea of in C++, just for something simple as binary search. This is how you do array. This is how you do variables. This is how you call a function. And inside the function, for example, here, this is how you write the loop. And in the first example, we saw how you can use for loop. This is called a while loop, but this part is pretty similar to Java. Not much to talk about. And if you need to return some value from this function, then you could use this return, and the return type should match the return value. Okay, so that's the end of the first session. This is the first one. This is the baby step, and all we talk about is how to compile source code, why we compile source code, how we compile source code with different ways, and some very basic semantics with the example of the searching algorithm, um, how you can write the simple C++ code like that. The second part of the lecture today is about memory. So let me switch there. Memory. Okay, and so for this part, we are going to do the coding at the end. In a computer system, the way to think about memory, I have this analogy that you could think of uh, memory or a unit of memory as a mailbox. The memory is like in the mailbox, what are the things related to a mailbox? Well, it has an address, it can store things, and also it has a size limit, right? It can only store a certain amount of things. I cannot put my car into the mailbox. That's ridiculous, but you can store mails. And in the US, if there's too many mails, and it reaches the capacity of the mailbox, the US post office will take that away. So the mailbox has a size, a limit, and it has address, right? The computer memory, you can think of that as we have a bunch of places where we can store things, and to make it easy to track, we split them up into some unit, and each of the unit would be sort of similar to one mailbox. And if you put all these units together, you end up with a bunch of mailboxes. And in this case, the size of this unit would be the same. So each mailbox here can store the same amount of things. And if we um, need to store something larger, then in real life, it's not possible to put something larger into multiple mailboxes at the same time. But in the computer system, we could say, I'm going to pair the first four mailbox as a huge mailbox, and we can use that to store things. Um, the storage or the unit or the basic unit of data in the storage system or in any computer system is called a bit. It's just a one number that's 0 or 1. So that's just one bit that can be used to store. And that's probably too small. So each unit in the example earlier, that's one mailbox. Each unit of that is it normally consists of 8 bits, and the definition for that is a byte. So a byte is just 8 bits altogether. That's the usable unit that in the memory system. And the memory is just a bunch of bytes. You can think of that as a pool of bytes, a collection of bytes. Um, and the memory system would consist of code and storage, which is data, right? In this example, we can see it's a simple code, and this is sort of a data section of the code. You can imagine in the memory, we'll have, because here we have 5 characters, right? HELLO. Each character can be represented by a byte. So this is HELLO. How do I know that? In fact, in the code, if we set a breakpoint here and we stop here, C-line has this cool feature called the memory view. You go there, you could literally see that in the code section, we have this hello stored in there. That's this part. And this gives you the hex numbers of each character. So for H in hex, um, that's a 68. And if you do a quick ChatGPT and convert 68 to binary, this is a binary. So that's why I say um, just this string hello, the actual storage is 011010000. This is 68. 68 represents the character H. Okay. Um, with that, so basically, the next thing I want to go over real quickly is um, if you imagine your computer system has what we have these days, normally like 128 gigabytes or 64 gigabytes, you have a lot of gigabytes in there. Um, with that amount of memory, how does the code use it? Right? If we have different program on my laptop, there's Windows running, or not Windows, there's the operating system running, there's the Outlook running. Sometimes I have WeChat. We have a lot of programs, we have a lot of code running together at the same time. And they are all using that memory. If that's the case, then how does our code share memory, right? If you think of the memory as a pool of bytes, then the code would ask for would sometimes use some bytes, and some code would use more bytes, some code would use less bytes. So how do we manage this pool of bytes to make sure every code can get some memory to use, and we can keep track of which part of memory is used by which code, right? Imagine it's sort of like in this case where if we have like a big office building and we need to put some people in there, we need to put chairs and we need to have some space for people to use. What do we put in there, right? If we have a table chair and that's for one person, then if we have more and more person, do we just fill the space with all the table chairs for each person? That may work, but sometime for office, then people need a place to share, right? They need to have conference. If we fill the space this way, every space is private to that person, then how do we find the space for a conference or for meetings? Okay, then if that apparently doesn't work, then we need to use some of the space for meetings. So the top part we are looking at, this is essentially the shared space. The space can be shared by it does not belong to a certain people. You can use it, you can borrow it, but once you're done, you need to return that and so other people can use it. Essentially, the space now is the arrangement is that there should be private space, there should be shared space. That's actually the same case with the memory system. And uh, for this pool of bytes, it's not just one pool that people just get memory from. It's actually split into the private space and the shared space, or the private group of bytes, the shared group of bytes. And real quickly, for each function, for example, if we have this full function, every function that's running will come with its own memory to use. So there's a small piece of memory. If we run a function, the function will be able to use that memory directly. Um, that's think of that as the private or the chair for each person situation. That's the small piece of a small pool of memory that the code would get access to. Other than that, there's also a bigger pool. This is the shared pool. And the shared pool in this case is larger than the private pool for this. There are names for them. The smaller pool that come with each code, we normally call them stack memory or simply just stack. And the bigger pool of bytes, we call them heap. You might remember the word stack from 143 when we are talking about the abstracted type. Stack is sort of a first in, last out data structure, right? The stack here, the reason this is called a stack, just a piece of a pool of memory, a pool of bytes is called a stack. There's a reason why it's called that because it's sort of related to that first in, last out data structure. But that part is a bit beyond 342. Or if you're curious, you can ask ChatGPT why this is called stack memory. But there's a reason behind this that why this is called stack. But again, the smaller pool of the bytes that come with each piece of code is called stack. The larger pool is referred to as the heap. This is important for us to write C++. We need to remember what kind of memory is allocated from where. But here I want to give you a quick analogy of this just so you have some mental image. The difference between the stack and the heap is sort of like our wallet in terms of money. The stack is sort of our own salary. Remember I said that when the code runs, it has a piece of memory that it can access directly. The word directly, in this case, in terms of money, if we need to buy something cheap, you buy from Amazon, you buy something for yourself, those small things you can just reach out or you can just reach into your wallet, buy something, just get the money and buy it, right? It's your money. So there's no process involved. You just take it out and just use a credit card or cash to buy it. The problem is that if we are trying to buy something large, in this case, a house, right? If we haven't inherited a huge amount of money from a rich uncle or something, if we are just relying on the salary, that we can simply just reach into the wallet, get the cash, and buy a $1 million house. It's not possible, right? So what can we do? Well, one option is we can wait 30 years. Once we have enough savings, then we have $1 million and we can buy the house. Um, that's one option, but that's not the option people normally use these days. The common option is that even though we don't have that much money, we know someone else or something else has enough money, which is the bank. So what we can do is we can take out a loan. So we can borrow the money from the bank, and we use that money to buy the house. And we will spend the rest of the 30, 40 years to pay off that loan. Um, the benefit of doing this is we get to enjoy the house for 30 years instead of just waiting to buy that house for 30 years. That's the positive side. The downside in terms of money is we have to pay interest on this, right? You're not really paying back the exact amount. That's how the bank makes money. We have to give something additional. So that's the case in terms of money. In the computer system, fortunately, there's no interest. All the In this case, the bigger pool, we treat the bigger pool of the memory, the heap part of the memory, we treat that as sort of the bank. And the memory that comes from your code, we treat that as ourselves or as the wallet. So in this case, the bank, the quote unquote the bank, the heap, all it asks for is once you're done with however much you borrowed, return it, right? In this example, well, the like for this code, what this code does, it doesn't really matter. But we can see that in C++, if we are borrowing money, we are using the keyword new here. You can see here, we're saying we are borrowing, or I need two arrays. And the first one is size n1, is integer type. So essentially, we need n1 number of integers. And the second one is we need n2 number of integers. So altogether, we're looking for n1 plus n2 number of integers. We need to borrow that piece of memory to store data. And the way we do that is we're using this new keyword, and this is going to return the address for this piece of memory. So when we write code like this, what happened behind the scene is this piece of the memory comes from the heap. And whenever you see this new, just think of we're taking out a loan. We're taking out the loan of a piece of memory from the heap section, which is essentially the bank section. And but the memory here, we get to use it. And similar to the real life, once we're done with the code, once we're done with the piece of memory that we borrowed here, we need to return it. And the way to return memory to the system, to the quote unquote bank of memories, is using this delete keyword. In this case, the L and R are both arrays, so we cannot just do delete L. Otherwise, it will think that it will just be one element. The bracket here just indicating, hey, we are returning an array of elements, an array of integers. Same ways they are, we're going to return an array of integers from this R. By doing this, the memory we borrowed would be properly returned to the system, and that piece of memory would be able to be used by other program. Okay. Yeah, just a quick summary. For this part, the key thing is I would suggest just keep this mental image of a bank and your wallet. The bank is the heap. This is where it has more memories, and so you can borrow it from there, and you just have to return it once you're done. The local memory or so-called local memory is something that each program would come with some piece of memory. It's much smaller than what the bank has. Your wallet has less money than the bank. So the stack memory that comes with each piece of code would be smaller, but you can use it directly. So there's no loan. You don't have to return it. Like if we are talking about this function, right? We have this variable C, we have this variable A, B. All these variables are allocated from the stack, so they are really fast to use. We're not borrowing anything, so the space used to store the three integers A, B, and C are from the stack memory. In the other case, if you anywhere if you use new, you're borrowing memory from the heap. That I can already tell you that's a slower process. Same in real life, right? If you want to buy something with the money in your wallet, it doesn't take much. You just go there, get the money, get the check, get the credit card, you use it, right? If we're taking out a loan from a bank, it's not something you could do like within 2 hours. It takes days, it takes weeks for that process to happen. That's in real life with money. With memory, same thing. Because the heap part is shared by all the programs, your Outlook, your game, your IDE, whatever is running on your laptop, those are constantly returning and borrowing money from the heap. So the heap has to have something to make sure like to track off, okay, you're using this part, they are using that part. When you return, only this piece will be returned, would be marked as they can be used by other programs. So there's a lot of keep up, there's a lot of management involved for this heap part. Um, Pretty funny. The thing is, as I said, the stack is relatively small. The heap is larger. And there's a command that you could run to see how much memory each program has, right? On my Mac, it says is the command is this. It tells you it's about 8 MB. And so what I want to show you here is actually there's some way you could actually see that for yourself. So treat this as a fun exercise. And the thing we're trying to do is find out how much stack memory is for each program. Okay. And what we're going to do is we're going to essentially keep allocating memory from the stack until there's no more memory left. And we know that stack memory, like the memory would be allocated from the stack if we cannot use new here. If we use new, that's from the heap. We cannot use that. So we could say, let's just have an integer data array. And if we have 1024 elements, how much space does this cost? We know that the size of integer is 4 bytes. 4 bytes per int, and we have 1024 int. So altogether, that's 4 KB, 4 kilobytes, right? And if we keep allocating 4K, 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 4K until there's no more memory, if we count how many times we could allocate this 4K, we get to find out how much memory. And especially on this machine, if this is telling you it's about 8 MB, then we should be able to confirm. And the code here, once it's done and we run it, it should crash and show that there's only about 8 MB of memory to use. How do you do this? Um, well, if you think about it, you could keep doing this, but I don't know how many times this is going to work. The solution I would suggest is if we put this into a function, let me put this here. And the full function, actually, we need a return type, which is void. It doesn't return anything. Put a void here. And instead of allocating memory there, we're going to put this here. Okay. So the main function would call the full function, and inside the full function, it will just allocate some space. Then can we do this? For example, can we just write a for loop and I don't know how many times, let's do 8,000 times. And can we do this? And if the memory is used up, then the for loop probably won't finish, and we can count how much what's the I at that time, and we know how much memory is used. Can we use this to figure out how much stack memory? So if I print out the I %d integer, and if I print out the I, and let's run this. And we see that it sort of finished successfully because it went from 0 to 799. Those are 8,000 times. And x equals 0 means there's no other issues. Normally, if you see a non-zero x code, that tells you there's some kind of memory issue. But so far, it doesn't crash, right? Is this because we haven't reached the limit? So let's do some math, right? If for 8 MB, that's 8 times 24. That's how many kilobytes? And um, like every array takes about 4 kilobytes, so divided by 4. So it's about 2048 times. And here is about 8,000 times. So it should be beyond that. So this means it's not crashing. And the problem here is this. When we use stack memory, the stack memory will be allocated for a certain scope. In this case, it's just this function. So when the function returns, this memory is automatically returned to the system. It would be nice if our wallet works that way, but in this case, we use this space. We don't have to do return data because this is on the stack. So once the code finishes, once this piece of code finishes, it will be returned to the system. And that's why if we call this in a loop, we are essentially just using 1024. We're essentially just using 4 kilobytes. Okay. So we need to keep allocating memory. Once we have a piece of this, we need to hold on to it, and we need to allocate more. We cannot the full function cannot return until we find out our answer. So how do we do that? How do we run this function and then run this function again before the first run finishes? Recursion, right? So instead of doing this, we could just have the function call itself. And when we call the function itself, the memory allocated here is still there. It's still on the stack, but now we're calling the same function. It's going to ask for another 4K. And before this is released, we go in here, it's going to ask another 4K. All of a sudden, we're using 12K. And we keep doing this until something happens, until something crashes. And we need to, okay, so before we do anything, let's just run this, see what happens. Here we do see that the exit code is not zero anymore. As I said, that means the code is running, and here you can see that it's interrupted by signal. This interrupted is the operating system killed the execution. The operating says, I cannot run this anymore. I cannot let you run anymore. I'll kill you, and the code finish it. Okay. So that's actually what we want, right? We know something happens that triggered the code being killed by the operating system. It's likely that this is because the stack memory is used because we keep allocating 4K, 4K, 4K until there's no more stack memory left. So how many times did we allocate it? To find out that, we could just have a static variable, number times called. A static variable is it belongs to the function. It does not belong to the execution of a certain function. So if we have this full function, we'll just have one variable. And the cool thing with static is the second time you call the full function, the value of the number of time called from the last call is still there. This allows us to do this. So we'll keep incrementing the number of time calls. And in fact, we're going to print out the number of time called. So we know that it will just, we can see that it goes from 0 to 1. And we're curious how many times it's called before the code crashed, right? So let's run this. And we see that it's about 2,000 times. And if we bring back the calculator, so 2,000 times 4K, that's that many KB divided by 1024. So that's it. We can see that it's about 8 megabytes. So this simple example, which actually in my class, I normally use this as sort of a test program, test code in the final exam or midterm exam. Just with this simple recursion call, we are able to confirm the stack size for each program is actually about 8 megabytes. Okay, that's pretty small. That's really small, right? And the question you might have based on this is, okay, if the stack size is about 8 megabytes, how big is the heap? Remember, the heap is the bank. The heap is supposed to have way more memory than our wallet, than the stack, which is similar to our wallet. The answer is there's no limit, actually. That's then corrected. The limit is really two things. One is how much physical memory do we have there? If you put a more physical memory chips into the system, you get more memory. And all those would be part of the chip, except the part for the stack. And the other limitation is, remember we have all these bytes, right? If you have a big pool of bytes, then how big is that pool? How many bytes can we put in their pool? And the pool size is determined by the address size. The address is just how many bytes can the system represent. In this case, at some point in history, the number of bits that used to represent the address is 16 bytes, or 16 bits. So 16-bit, if we have 16 zero and ones to represent how many bytes we can have in the system, which, by the way, is if you recognize this machine, this is kind of this kind of Nintendo console, the game console. They are actually, that's what they have. They have 16-bit of memory address, which means in their memory system, the number of bytes is just 2 to the power of 16. That's how many different address or how many different bytes can be represented in the system. So that goes from The first one is all zero. The second one is all zero but one. Second one is all zero but one zero, so on and so forth. If you count how many of this are there, how many different of this are there, that's 65535. That's how many are there. That's how many bytes the system can have, because if you have more than that, if you have more than 64 kilobytes, even though you can put that in the system cannot recognize them because it cannot count anything higher than that. Um, so 64 kilobytes is how much memory we can use in the system that has like the system address. The address of the bytes would be 16 bit. If you think about it, it's very interesting. The 64 kilobyte, that's really small. That's really, really, really small, right? Like how much memory do you have in your iPhone? 64 kilobyte is smaller than if you try to do anything, it's unimaginable that we could do anything with 64 bit, with 64 kilobytes. Well, as I said, those Nintendo game console, that's what they have. That's all they have. Like if you have ever played Super Mario, that's how much money or how much memory the game has. And there's a very interesting video on YouTube talking about this. So I'm going to show you this real quickly. And they did some calculation. Imagine if you could just store one screen of this game with all those pixels. And for each pixel, you need to represent colors. So all the color, you need a certain number of bytes to represent the information. But long story short, for one image, one screen of the Super Mario game, it takes 15 kilobytes. 15 kilobytes. Altogether, we have 64. If that's just one screen, how is that even possible? How does the game even work, right? How many screens are there? It's definitely more than one screen. It's definitely more than let's say four screen, right? The fourth screen, that's already 60 kilobytes. So that's already going close to the limit. And here's a video. I find it very interesting because it shows like with the limitation of the physical resources, what the engineers did to optimize this machine. So we, at least from my childhood, we get to play all these awesome games, right? So just take a look at this video. It talks about how they managed to program all this awesome game with just 64 kilobytes of storage. Just to give you some idea, 40 kilobytes is equivalent of 2 seconds of music. 2 seconds, right? So apparently that's too small. And if you check your system these days, by the way, in C++, this is how you can check a size of the address. The computer these days, normally they don't have 16 bit of address. They have 64, so about 4 times longer. So as you can see here, this is a 64-bit address. That means the number of bytes that can represent it in the system is now 2 to the power of 64. That's 2 to the power of 34 gigabytes. I don't believe anyone on the planet of the Earth would have that much memory in their system. So this is just the upper limit. This tell us that however much memory chip you put into your computer can use it. It's really hard to get to that amount, 2 to the power of 34 amount of physical memory. Okay. Just a quick summary. Okay, so far we have been talking about the two kind of memory in the system. It's think of the entire memory system as a pool or a collection or the big amount of bytes. Then it's split into two sections. One is the stack, which is a private section that come for each code, and the size is small. The heap is the bigger pool. The analogy is stack is our wallet with smaller amount of money in it. The heap is the bank. And if we need to do something, if the code need to do something with more memory, similar to the case where if we need to buy something large like a house, then we borrow the money in terms of computer, it borrow the memory from the heap, and once it's done, we need to return that, right? The last part of this, I want to just a quick discussion. You may have this question. We said that there's a heap, there's a stack, but it didn't really answer the question, why do we need two? If we have a pool of memory, um, why in the first place we need to have two sections? Can we just have one? And why do we need to have a slower one and or the smaller one, the stack? Can we just have one? And whenever the code need to do something, we take the memory from the heap, right? So we still haven't answered that question. And the real answer for that is that in addition to the size different, there's also a speed difference. So as well, I think we talk about this, from your wallet, if you need to buy something, it's fast, right? You just get your credit card, get your cash out. If we're buying something large, we need to borrow from the heap, then it's slower. If we need to file a loan, we need to get approved. In terms of the computer, using memory from the stack is really fast, and using memory from the heap takes some time. It's a little bit slower. The reason for this to be slower, it really comes down to that if there's any resource that's shared, then something need to be there and to manage that. So here I give you a quick example. Suppose we have two program, we have a bunch of bytes for them to share. So this is the heap. And the first program says I need to have 3 bytes. The second one says I need to have 5 bytes. Those are allocated for them. And the first one come in and want 2 more. And the second one come in and want 4 more. So the memory is about is something like this once everything is allocated, and then the first one finish and exited. So now the second one come in and still running, and all of a sudden it says I need 4 more bytes. Just based on the illustration here, you can see that do we have 4 more bytes in there? We actually do, right? We have 3, we have 2, that's 5. Or we can take this 3 and this one 4. The problem with this is that if we want this, if all this memory are right next to each other, it's relatively easy. But now they are separated in different locations. So if we need to allocate, still be able to allocate the memory like this 4 bytes to this program, we need something to at least bookkeeping, right? We need to keep track of which memory is used by what. If not, then we don't have 4 consecutive bytes, and there's no more memory. So with that, that's just to still we're trying to explain why it's slower. And it's slower because when a bunch of things are sharing resources, then we need to have something to manage the sharing, and that management process takes time. So it's a slower, and if we just use this, if we just use a big pool of collection or big pool of bytes, then we like every memory access would be slow. Which is not necessarily ideal, right? If we're just if the code does not really use big large of memory, then we don't need to bother. We don't want to bother this management process. So that's why for the way the memory system is designed, there's 2 sections. One is the stack, which is slower, which is faster but smaller. The heap is the shared pool. It has more memory, way more memory than the stack has, but it's slower. Depending on how you are using it or what your code is trying to do, you can pick and choose. So if you don't use much memory, then your code can run faster. If you use more memory, then your code not only will run slower, but it will have to keep track of getting the memory and returning the memory. Okay. So that's pretty much it about the concept of that. And I want to do a quick demo of how that relate to coding. In C++, Um, let's say we have a variable, and the variable is the integer and type 10, with a value 10, right? Um, if you remember from the concept, each p or each byte would have an address. And especially how many addresses are there would determine how many bytes we can have, right? If it's 16, it's 64 kilobytes. So the address, how do we get the address? In C++, for example, for this variable, we know this is 4 bytes. And the address to the first byte, if you find the first byte, you can find the other 3 bytes. So it's only important to get the address of the first byte is can be get we can get that by doing this. Um, First of all, this is the variable name. The ampersand here is saying take the address of this variable and store that in, I'm going to call this PTR pointer, store that in another variable. And the variable we use to store the address the type is int star. And whenever we have a star in the type, we call this a pointer. But a pointer is nothing just another variable. And the purpose of a pointer variable is to store the address of the memory location. This is an integer. We get the address, which is the in this case is a 64-bit number, and we store that number into this variable called PTR because the type of this is int star. It gets a bit confusing at the beginning, but if you just treat this, whenever you see star, you just treat this as the one thing. It's one single type. This is a type called integer. This is called type of pointer to an integer, address of an integer variable. Um, when we have the pointer, we could do a few things. For example, pointer is the address. If you have the address, you can go there and change whatever is there, right? If I give you address of my house, you can go there, and for instance, you can feed the pet. You can feed the cats for me. So with that address, you get the access. Given that suppose I give you the access key to the house, but you need the address to find out where the house is. In this case, we could use the pointer. For example, you could do equals 15. This is probably one of the most confusing part. You see the pointer here, and you see this. As I said, if you see it this way with the type at the beginning, the real separation is sort of here. This is one thing. This is another thing. Actually, this is another thing. So the separation is there. So this is saying this is a int star type. This is a variable name. This is a variable value. When you see this, there's no type. It's just a star. This is to say, just go to the address pointed or stored in this PTR variable, which is this, and put 15 there. Okay. And so this is equivalent of saying var equals 15. But we're doing this without using this var variable directly. So at this time, if I print out the variable, let's run this, you see that it's 15 now. Just to show you, before we change it, we print again. So now we have two of them. The first time is 10. We changed it by going to the address and set the value. And now we print it out is 15. Okay. So you do see that with the pointer, now you have access to that variable. So the variable really, if you think about that, the mailbox, right? The mailbox, the var here, the 3-character var is just a name for that mailbox. A mailbox is nothing but just a space where you can store things, and it has address. Those are the 2 pieces of information that's the most important. The if you give a name to a mailbox, it's just a name. You can refer to as the yellow mailbox, for example, but it's just a name. Speaking of names, another key concept in C++ is called a reference. If you remember from Java, it also has reference, right? So here I want to make sure we get this part. The reference in Java, it means pointer. It sort of means the same. It's not the same concept as pointer. It's not the same, exactly the same as what the pointer is, which is the address, but it's similar. So in Java, when you see the word reference, it means address, or the quote-unquote address. In C++, reference means name. And more specifically, remember I said a mailbox, you can call that a mailbox, call that a yellow mailbox or whatever you want to call it. That's what a reference is. By saying that, you could give different names to the same mailbox. Here in C++, you could give different names to the same variable. So how do you do that? In this case, let's say we have this. Remember I said this is a type. It's the pointer. It's a variable of this type that store the address of int, right? This is another type. The type is called reference, so let's call that reference. And the reference is a name, as we said here. So the reference has to be attached, quote unquote, attached to something that already existing, right? In this case, let's say we have this variable, so we just put the variable here. So now ref, it becomes another name for that mailbox for that variable. So if we do ref equals 20, and we still print out the variable and run it, you see that, oh, now it becomes 20. So the reference is really just a different name. I normally call that a name tag of a variable. And from actually the implementation perspective, from C++ perspective, a reference is just a syntax sugar so that the people does not have to use pointer. If some people they're not comfortable with pointer, you can use reference. From where I came from, I started as a C programmer and then move on to C++. In C, at least when I was using it, there's no reference. It's always the pointer. So it actually took me a few years to get comfortable with the concept of C++ has reference. And I keep on wondering why. Why do you need a reference? If you can do everything, like everything you can do with reference, you can do it with pointer. Why do we need a reference? And the reason really is just to it sort of can look cleaner. So this looks better than this because there's no star. It's also true that for instance, if we have a full function, I'm going to do it the other way. If we do the full function and we put the variable here, and this will create that for me. So if we want to do var plus plus, this will increment var. So let me change this to a different name. Increment by one. Okay. So if this function is what this function is supposed to do is to increment the value we pass in by one. If the code is written this way, it's not going to work, right? Because C++ is passed by value. So when we call this function with var, we are not really passing in the variable var. We are passing in the value of var, which is 20. And so this is a different variable. So we can call this a different name, like XYZ, that would be still the same. So this XYZ would have the same value 20 and add to it. Also, by the way, this is, if you remember, this is allocated on the stack. So once this function returns, that variable XYZ is gone. So the way it's written, when we call this function, it does not really affect the variable there. If we want this function to actually be able to increment the variable here, then we have two options. One is we can pass in the address. Remember, once we have the address, we can change what's there at that address. So if we change this to a pointer, then we take the address, we pass it in, and here we have to use this to say whatever is there plus one. Okay. So now if we print out this at the end, we see that is 21. So that's what you can do with pointer. As I said, the reference is sort of a syntax trigger, which just means if we don't want to use reference here, we could also do, if we don't want to use pointer there, we could use reference. The benefit of using this as a reference is when we call it, we don't have to do this anymore. We can just pass in the variable as if it's just the value, but in fact, we are passing in the essentially behind the scene, we're passing in the address, but we're really passing in the name. And inside the function, we don't have to have that star. We can just do it as is. And if we run this again, you see that it's still 21. So the reference and pointers, with reference is the code can look a bit cleaner. But still, if we don't have a reference, then like anything we can do with reference, we can do it with pointer. From function perspective, there's no huge difference, or there's no difference. Just from the way code looks, the reference is a syntax trigger that can make things look better. Okay, so that's pretty much it. Once you understand the concept of stack, heap, then or also the pool of bytes, that's the whole memory and the memory space and the memory address. Once you understand those, pointer is nothing but a variable that store address, right? And from that address, you can do a lot of things with it. Okay, so with that wrap the second section, which is the memory system. Okay, for now, let's move on to the next one, which is OOP. And OOP, as I said, is pretty similar to Java. So this part, I'll just explain some key concept, and we're gonna take a look at some code quickly, and there will be it. Okay. And let me get a slide. Open OOP. Okay, so OOP is the history of OOP in C++ is that the C++ take a lot of things from C, which is not OOP, and it took that and essentially it added the concept of class and the OOP to it, or a class and the instance to it. Comparing the OP with the object-oriented way of looking at the world with the functional way of looking at the world, those are just two different mindset. In the functional way, it treats everything as steps. Think of that as the sort of a cooking recipe, right? For a cooking recipe, all you care about is I do this first, I do that, I'll take the powder, I'll do this second and third, and at the end of all this step, you have the job done, you have the cake. And so that's the way of thinking of the world as functions, as steps, as procedures. The OOP in comparison is it's going to treat everything as object. So with the same example, you can say the egg is object, like all the ingredients, those are objects. And the step would be just the one object interacting with another object. So the object OOP way is really just treat everything. That's why you see in Java, the entire language is supposed to be OOP, so that if you just have a main function, they will still put that into a class. And that class sometimes is called main, right? You always have a class. So those are just two different ways. And OOP is not always the best way to write, or it's not always the best option. There's a lot of debate these days. between OOP and function. There's more ways to writing code. So depending on what code you're writing, OOP is not necessarily the best one. So in OOP, key concept is the class and object. Sometimes the object is called the instance, but the key difference is still the same. The class is sort of a blueprint, a template, a concept of something. For example, cat, right? And the object is just a concrete implementation of that class. It's a specific cat you could actually touch. But the concept of a cat, it just tells you what a cat should look like and what a cat should do. So here is the code in C++. If we were to write a class for cat, it should be pretty easy to translate this from Java. This is the base class. This is the derived class, and there's a public, there's a private, there's also constructor, copy constructor. Those are exactly the same concept from Java. This is how you can use. Here in this part is a little bit different. The way it's shown here, this is declaring an object of type cat, right? This is an object. But you cannot do this. We cannot do this in Java because in Java, we always have to say cat Chloe equals new cat with the constructor. Because in Java, there's no, it doesn't allow really just the stack memory allocation. This is saying that this is creating an object on the stack. So in C++, you can do that. Here, there's no new keyword, right? You see, so we're not borrowing money from the heap. We're just allocating an object, allocating space to store this object on the stack. Similarly for this object on the stack. And if this is an object on the stack, we can use dot. This is similar to Java. We could also use this to get the address. Once we have the address, now we have the pointer. And remember, pointer is just the address of some variable. In this case, the variable is an object. So that's a pointer. And for pointer in C++, we use this way to say the per function from the object with the address stored in this Coco variable, or actually stored. The object is the Coco, and we get the address, and we call the per function from the Coco object. So that's the encapsulation, and this part is the same. So I will not spend too much time on this. And there's also setter getter, basically private. You can access from that. The private is for member variables and the member functions. If it's public, then you can access that from inside the class or outside the class. If it's private, you can only access that from inside the class. So I'll jump through this. Then there's a concept of inheritance. This part is where I'm going to stop. Inheritance is saying we can have a class, but sometimes different class would have something in common. In this case, we can have a dog class, we can have a cat class, but you have the name color, let's say age for a dog class, and we can have the name color age for the cat class. It's a bit tedious if we have more pets like this, for example, a lizard or a rabbit, right? They all have name, color, and age. And a easier way to not have to repeat all those information is just to create a base class where we call this derived class could store the common things in the base class. And by having this, if you look at this example, at the top, that's the pet class. And we have the name, age, and color in the pet class. And then we have the dog class derived from the pet class. So here, all the things you see, those are things specific to the pet, or the things you specific to the dog. And for the cat class, it doesn't really have anything specific to. It doesn't have any member variables that are specific to it, but it does have this per function that's only in the cat, but not in the pet. So this is called inheritance, and this is how you can do it. And this is I want to call this out. C++, if you call the derived class constructor, then naturally we want to call the base class constructor, right? Because the derived class constructor does not have constructor for name, color, and age. Those are in the base class. So this is how you can call the base class constructor from the derived class constructor in C++. Okay, so I'm gonna stop here, and there's more things to inheritance. There's in Java, remember there's abstract class, there's an abstract function. In C++, it's called a virtual function, and it allowed you to do more cool things like polymorphism and all those things. Those are very useful, actually, for software testing, and class in general is going to be used a lot for representing as abstract data type. For example, a tree, right? A tree has a bunch of nodes. Each node would be a class. Then the tree itself, you could also write that into a class. A linked list, each node of a linked list is also a class. So all those the class are very important. It's also important for us to have a solid understanding and a solid practice how to write C++ code with this. Um, and being able to have to represent those data type in C++, and we can use the data type to do things that we want them to do. We can store data in, for example, a binary search tree, so that give us much better search performance and the insertion performance. And then, for example, based on there, you can build more complex data structure and achieve more things. So altogether, as I said, I'm going to stop here. So that will be the end of this Bootup session. Just a quick summary. Um, we are talking about C++ here. The goal is not really to learn all the things about C++. The goal is to understand why we are learning C++. And the answer to that is really C++. When writing code in C++, we need to understand the system behind the scene a bit more. So C++ is a window for us to see or access or understand more about the computer system. Um, so the goal is not really just learning this language. And from my perspective, it's a CAP. It give us a chance to practice our critical thinking, and problem solving, and also being able to see and understand and know more about the system. It give us a chance to appreciate more about how the complex system is designed. Um, so that opens the door for us to solve the higher level of problems. So that being said, I have this opinion about the 342, which is that writing code to solve the problem is not really the goal, especially these days with AI. If the professor give you some code and you want to, you can use AI to get the answer pretty easy. So getting the right answer is actually not that hard. That's not the purpose. The purpose is all the things we are learning, which is the problem solving, right? If you have a problem, the training you get from using a program language, understand the problem, and come up with a solution, that process itself is what you pay the money for the college. That itself is what you can learn from your professor, from other students, from working by yourself. Those are the things that will go a long way. So just focus on treating each process as a learning process. You're learning how to solve problem. You're learning how to decompose the problem into smaller unit so you could apply what you learn from the class to them. So yeah, just that just goes to that the whole process is really for us to learn the thinking process, and the programming language C++, that's just a tool for us. So do not have to go too far into the programming language. In the future, if your work demands that you use C++, you will get a chance to learn more. That specifically, I want to mention, for example, in C++, there's smart pointer. Um, In my class, I don't use them. It's not because they are not useful. It's because for learning, they're not useful. Well, we want to learn the pointer because through the pointer, you can understand the address of the memory and all those things. Smart pointer is really just for production, right? You're really producing something for customer to use. And in that situation, you want to care less about understanding. You should already understand those, but you want your code to be robust. You want your code to not have memory issues. In that situation, yes, go ahead and use whatever C++ provide. But for the learning, it's really the process that matters more. Okay, so with that, I would conclude this session here. And thank you for sticking to the end. Hopefully, this is helpful, and I wish you the best luck in your 342.